Hello, welcome to VCAT. This is the presentation on how does an asphalt plant actually work. If you want to refer to your study guide, Asphalt Plant Level 1, it'll be in Chapter 3 that you'll need to refer to. And how we're going to start out is we're going to start out plant process and operations. Basically, the class objectives are going to be basic plant operations, what is the plant process, and details about the plant components, along with a lot of terms and points of interest. As you can see in this picture, this is some of the models that we use for training. And this is a stationary asphalt plant. The models give a good representation of a clean asphalt plant that you can actually go in and take a look at the components without the dirt and the debris and the mud and the grease on the components. So as we go through this, we're going to refer to these models many times during this presentation to give an adequate determination of what's going on with the plant. Here's a portable plant. As you can see, the footprint's a lot smaller. One of the reasons for the portable plants is highly portable. They can move them around easily. You can see that everything is pushed together a lot tighter space. They are still capable of high production rates, all the way up to around 500 tons per hour. At the center of every asphalt plant is a control house. This is the central location for controls. It manages all of the plant operations. These operations include the motor control, start, stop, burner control, mix process, and load out. These controls could either be relay logic or PLC controlled. If you look in the lower left-hand corner, that is a relay logic picture of a relay logic plant. In that relay logic plant, if you notice, there is lots of push buttons, consoles around the entire perimeter of the control house. 20 years ago, this was the normal, and this is what you would have saw in any asphalt plant. As we move forward, in the last 20 years, lots of PLC controls have been introduced. These PLC controls have changed the demographics inside the control house tremendously. Instead of having several consoles around the perimeter, it's very familiar to just have two computers processing the whole control inside. It's been a change for operators over the years, but the PLC is being pushed and mandated a lot of times by the state. Even on the older relay logic systems, when you looked at a blending control, that particular blending control more than likely had either a proprietary blending control or a PLC blending control associated with the push buttons. Some people ask, what's a blending control? The blending or mix control allows the operator to enter a job mix formula that can control and properly proportion aggregates, recycle, asphalt, dust fillers, liquid asphalt to meet the required specifications. These blending controls have changed a lot over the years. Back when asphalt plants first started, if you was at a batch plant, you would pull levers to get the ingredients that you needed, and they'd be weighed up on a scale, and you basically just eyeballed what come up. Now that you've got the computer systems involved, a lot more precise, mix specifications can be a lot more calibrated, everything can be a lot better mix quality. If we start with this process, everything starts at the coal feed bins. This is where your virgin aggregates are entered in. Here's a good representation of a 6-compartment coal feed bin. As you look at these coal feed bins, they're always going to refer to the one that's closest to the shaker deck or the conveyors as your bin number 1. That's where you're going to put your fine material. And as you move through those bins, the coarser the aggregate will get. So you start out with very fine, and then it moves down and you become coarser as you get back towards the end of that. And as we go through the presentation, we'll talk about that and the reason for that a little more. If you get a top view of the coal feed bins, this is a grizzly that you see on top of this. Some people ask, what's a grizzly for? Well, a grizzly is to keep all of the debris larger than the specified material that needs to be in that bin. You take sand, things like that are very fine. That's where you see your grizzlies at. The reason that you see grizzlies is because a lot of times roots, debris, sand that has congealed together and made a large ball, you do not want that type of material to fall down into the bin, and we'll talk about that too as we move forward. If you take the grizzly off and look down into the bin itself, you'll see that at the rear of the bin you have an opening, and then as you move forward that bin opens up a little bit. What that means is that it's self-relieving. And so it does two things. One, it keeps the bin flowing well, and then two, it keeps the bin to fall evenly. You talk about segregation. Segregation in a co-feed bin, as long as you've got good material, should be minimal. But when you move to a recycle bin or something like that, and you're not fractionating wrap, it is very, very easy to segregate the material. So that is the reason for the self-relieving bin. Here's a side view of the bins. If you look at this bin, they are equipped with vibrators. These vibrators actually keep that material flowing. They can be designed a lot of different ways. Sometimes they can be connected directly to the bin. Sometimes they can have a dancing plate on the back. And sometimes you can use bin butlers or things like that to keep that material moving. But these vibrators can be controlled automatically or they can be controlled manually. One of the things that a lot of people do is when they see no flows, they hit these vibrators to keep the material flowing. If you go to the front of each bin, there's going to be two things that you're going to notice. You're going to have an adjustable gate, and you're also going to have a no-flow switch. This adjustable gate does several things. You can increase or decrease the amount of flow that you get out of this bin. It's volumetric. There's a tach feedback off of it. So you can speed this belt up or slow this belt down and use that gate adjustment to change the flow or the TPH. Also, you have a no-flow switch here. One of the common things that happens at plants is that it's a maintenance item. The no-flow switch gets removed or it gets pried out of the way to where it will not show a no-flow at the plant. If you get that case at your plant, that can cause inconsistent mix, or it can cause mixes to be out of spec due to material that's fell into the throat of the bin. As we go back and look at the side view of the plant again, you look at your co-feeds, we talk about feeder delays, and we're going to talk about feeder delays and point of mix times a little bit as we move through the presentation. But some people may ask, why are feeder delays important? The reason that feeder delays are important is because they really can cut down on the amount of waste, and it can also increase the quality of your mix. One of the things that a feeder delay is, and some manufacturers will call them start-stop times, feeder delays, there's lots of different terms, but they all may mean the same thing. And basically, a feeder delay is from the time this feeder starts to it gets to the weigh bridge on the incline conveyor. So those times change. A lot of times at a plant, some customers will go in and say, let's make it 2, 4, 6, 8, and 10. Well, that's not really a good representation. If you get that time precise, then all of this mix or all of this material will come to the weigh bridge at one time. It'll be weighed correctly, and then as it's conveyed through the rest of the plant, again, all the material will stay close to each other. You will not get segregation, and you will really minimize the amount of waste you'll see at your plant. If you look at this drawing of the collecting conveyor, that's the conveyor that's directly under the co-feeds. That's actually where the first small amount of mixing occurs. If you look at that, this is the troughing idler for that conveyor, and you can see, well, how does it do that? Well, here's an illustration. Each bin deposits the material on the collecting conveyor, and here's the belt travel that you see. Here's your coarse and the other layers of material as we move forward. See the coarse material first. Continue the belt travel. And then we place our fine material on top. One of the questions a lot of people ask is, why do we put the fine material on the top? The reason for putting the fine material on the top is two things. First, it keeps that fine material off the belt. It reduces buildup. And it also reduces maintenance for belt scrapers and things like that. Also, it gives it a bed. That way it can stay up there and it mixes a little bit easier. As the material continues on, it's going to come to a scalping screen or a screen deck. These can be single or they can be double. They can have different mesh sizes in to basically reject the material that's larger, that does not belong in the mix. One of the things that it also does is this is the first time you get a little bit of gentle mixing, and we'll cover that. If you look, the material is layered and properly proportioned on that belt. You can see they're very close to one another, but they are segregated. You have your fine, then as you go down, the material gets a little coarser each time. As it hits the scalping screen, you get the shifting action, or you get a small mixing action, and you can see that it The unmixed material is now visually detected. You can see it. If you're looking at the incline and then you look after it passes through the screen deck, there's a big difference in the way the material looks. It's no longer segregated, everything has been mixed, and it's generally mixed, but it has been mixed. And you can see this representation of the material. Here's your distinct layers, and as it goes through the scalping screen, you can see here where it has the gentle mixing as it goes up the Weybridge belt. Here's the virgin Weybridge. One of the things that is unnoticed about the virgin Weybridge is that it's easily overlooked. One of the reasons is because it has wind guards. You can see these wind guards in this picture here. We're going to talk about them a little bit more. Right below that, and it's usually down on the lower end of the belt, you'll see what we call a gravity take-up. And that gravity take-up is used for one thing. That is to take the inconsistencies out of the belt. As a belt warms up, and a lot of operators are going to warm their belts every morning before they start the plant, the reason for doing that is to take the stretch out of the belt and the inconsistencies. And basically what this does is it just keeps tension on the belt to take those inconsistencies out. It stops belt hop, it starts a lot of different things, Some people may ask, well, hey, I don't have a gravity take-up on my incline belt with my Weybridge. Is that going to give me a problem? It very well could, but sometimes as long as you keep maintenance up well and you take care of your belt, you can do it without a gravity take-up, but it is much, much better to have the gravity take-up in place. Here's a good picture of the wind guards that we talked about. It keeps the Weybridge hidden, so it's easily disguised, and it usually is not maintained very well because of that. You can see, here's the reasons in this picture, and it gives a little bit of an illustration. If you can see the wind on the flag, how it's blowing that flag straight. If we did not have these wind guards here, we'd get belt slap, which would give you inconsistent belt readings when you tried to do the zeros. So it could cause you problems when you're trying to make mix. The virgin weigh belt is combined for all of the co-feed bins. The weighing is done by a combination of weight and speed. You have to have weight and speed for this. It requires alignment. We talk about string lining, and it also requires calibration. When you're talking about calibration, some of this is done through scale factors, some of it's done through constants, but every co-feed bin needs to be calibrated, and the virgin Weybridge does also. The signal from this device is transmitted into the control room for the process control, and that's where that information is stored, and that's where that information is used for the job mix formula. The virgin Weybridge is the primary scale on the plant. It is the primary scale. All other scales follow it. To go over the evolution of Weybridges, these are some old Weybridges here, Ramsey Weybridges. They are a very well-known Weybridge, done very, very good. One of the things that a lot of people noticed on them, they did have some mechanical inadequacies, and that was the rubber bushings in those. As those bushings wore, they would cause some inconsistent mixes. Here's a Barber Green Weybridge. It's a little bit different design, has a lot of weighing idlers. A lot of the designs are kind of built off of this. It had a flex point, or what we called a flex door here. As that material flexed, or that metal flexed, that's where the pivot point for the weighing idler was. The only problem with this style Weybridge is, as any type of metal, if you flex it enough times and bend it back and forth, it will fatigue and break, and that's what you would see. You would see broken flexors in this area of the Weybridge, and what that would cause is inconsistent mixes. Here's the load cell that you'll see on a Weybridge. This is more of an old style or a little dated load cell. It is a canister type load cell. One of the things about these load cells, they're kind of hard to find now. A lot of people do not use them anymore. One of the reasons for that is barometric pressure. Barometric pressure can affect these. You'll see a few other things too here. There's some insulators, that's these red items, and then you'll also see a cable that goes around that. It's for two things. One's for lightning protection, and two, if there's any type of welding or anything done on that conveyor, that it can actually direct that around the load cell and will not burn it up. Lots of times on the lightning strikes, the load cells and the tacks are what take the hit. Here's another model from our training facility. Kind of gives you a cleaner look of what you see in a Weybridge. It's a very small footprint. When we talk about Weybridges and we talk about weighing, we want to look at the weighing idler, and we want to look at the 3 idlers above it and the 3 idlers below it. When we talk about stringlining, that's what we're stringlining. We're stringlining all 7 of those rollers to be the same height. Some people will say, hey, I want that roller a little higher. No, I want that roller a little lower. You will never go wrong if you keep all of those idlers at the same height and you square them up to the conveyor. If you do that, you're basically just taking the inconsistencies out of the metal, which in turn will give you a quality mix, a very good weighing device. As we push through and look at this, we can see here this is the device for the test weight. You can have a test weight here. It gives the operator the ability to do a quick test to see if the calibrations are in. There is some pinch points and things here you need to be aware of. Also, when you do an inspection and you remove these wing guards, this is also areas for material to fall in, so also look for that. Here's a more new style S-type load cell. There's several advantages to this style load cell. One of the advantages is that it has some built-in lightning protection, which is always a good thing. And then secondly, it's not affected by the weather. Barometric pressure will not affect this load cell. You still see that you have the jumper that goes across it for diverting any type of electrical charge, and then also you still have the insulators to try to isolate it from any type of lightning that goes across the grounded equipment. As the material moves on up, it's going to enter into the drum. And there's something else that affects it. As soon as it drops off the head shaft of that conveyor, it gets affected by the exhaust system. And that's where we're going to go next with the exhaust system. Here's a double barrel plant. Lots of double barrels in the state of Virginia. You can see that we are actually pulling exhaust on it. And here's the drum itself. This particular one has a pug mill for external mixing, and you got your burner on this end. When we talk about the baghouse and the exhaust systems, this is a pulse jet baghouse. You can see here's the stack that comes over. This is pulling the fine material over, the -100, -200s. This particular one has an inertial separator. Here's the baghouse body and then the exhaust fan on the end. There's a better view of the exhaust fan. Years ago, what we would deal with on the exhaust fan is that we would have a damper control on it. And those damper controls were basically located right at the top of the fan. And you could use a set of louvers to actually move that, or radial style louvers to do that. Everyone has moved away from that, and they went to VFDs. VFDs are utilized throughout the plant. They're used on the coal feed bins, and those VFDs are just like that in a drill, basically where you want to adjust the speed by just speeding it up and slowing it down. So they're able to do that on the exhaust fan. It does 2 things. It reduces the noise tremendously, and then it also saves energy. Everyone likes to be able to go green. This is a great alternative to going green using a VFD, which is a variable frequency drive on these exhaust fans. And they've really taken that to a whole different level. Now we use them on drags, drums, and there's lots of advantages, energy savings being one of the most. Here's some views of some little older plants with some primary collectors. If you look up on the top, you got the knockout box, more of a conventional style. You can see that it's basically very high up in the air. The ductwork's up high, kind of hard to maintain and look at. Really changes the footprint of the plant. If you look down in the bottom, you got the vertical cyclones. They are still used to this day. We see a lot of manufacturers still use that. The thing that you do see is still you got the ductwork up very high, lots of crane costs and stuff if you're going to move that plant. So sometimes that is the way that people like to go, but they've changed a lot over the years. Everyone kind of moved to horizontal cyclones. If there's anything at all about the horizontal cyclone that was a downfall of it, and we still use them a lot today, is that they were almost too efficient. So we had to put skimmer plates in the bottom, and then you were allowed to adjust those skimmer plates to control how much dust you were pulling out of the drum. The new design, or what we're mostly seeing now on plants, is called an inertial separator. It's more of a elaborate word for an elbow. As you pull exhaust from the drum, as it moves down this high velocity air, the heavy materials hit these louvers and they fall straight down into the auger. And then you're conveying most of your -100s there. straight back over to the drum. Then as the lighter dust, the minus 200 gets conveyed over into the baghouse. And we've got some illustrations we'll show you a much better representation of what we got here. So what is the function of the exhaust system? Well, it's really to evacuate the drum. It's to get the steam and the products of the combustion. Everyone knows that we're drying this material. We're taking the moisture out. So as we dry that moisture out, we're going to get that steam, we're going to get that products of combustion, whether it's with natural gas on the burner, whether it's with fuel oil, or whether it's with LP. Other things that affect that too is the excess air. That's from the burner blower, and also any type of leakage air. And that leakage air can come from a couple of different places. So one of the things is where you see the aggregate introduced into the drum is one of the main places you'll see that. And a lot of times you can put a curtain or something like that up to reduce that leakage air. Here's just an illustrated photo that shows how the air is entered in. Here's your air coming in from the drum, going through the inertial separator. All of your minus 100s would fall here straight to the screw. Minus 200s would be pulled over. This is what we call your dirty air. That's the red arrows or the orange arrows. As we pull with the exhaust fan, we pull this dirty air up through, and then clean air exits the bags, and then we have the exit of the clean air. So they call this the clean air plenum, the dirty air plenum. And that's what you call your baghouse differential. One thing in the United States, every state has to go to a particulate test. And that particulate test is basically how many particles are you blowing into the air. Everyone has to meet that requirement. The other thing that you see in some states is you have to do flue gas analysis, and that really is how you tune that burner to be as efficient as it possibly can, and you have regulations you've got to meet on that. But everyone has to make sure they have their baghouse maintained well for the particulate test. When we talk about the exhaust fan, we're pulling on the drum. A lot of people call that burner suction. That's what we call it. And basically what you're doing is you're stabilizing that flame and you're evacuating that system. So some people ask, well, what's the ideal situation? How much burner suction or how much exhaust fan do you want to put on the plant? Well, it can change depending on what type of equipment you have. A good rule of thumb is just above a puff. Well, some people say, well, what's just above a puff? Well, as you're running or operating a plant, if you look at the burner end of the drum, if you get a puff of steam or a puff of like dust or something out the back of that drum, that means your burner suction is a little too low. So what you would do is increase that exhaust fan to give you just a little bit more burner suction. Usually 0.25 or 0.2 is the best, but sometimes you may have to run that a little higher or a little lower. If you have to run that extremely high, then you need to start looking at other places for a potential problem like leakage air or something like that. But just above a puff is what a lot of people, and that's how a lot of operators are trained. How's this measured? It's measured with a photohelic, and on the burner end there will be a pitot tube. And those pitot tubes can be located in a couple of different locations. Some of them are turned down 90, some of them are straight, but that is where that burner suction, the inches of water column is looked at. And we usually want to keep them around 0.25. So we're going to look at this animation of the baghouse. I'll try to narrate the dust coming through the system. Here's the tube sheet with all of your bags. According to capacity and CFM, the bag count will change. You will have to have extra modules for the larger capacity plants or if you're in higher elevation. This is the solenoids. This is actually where it's a pulse jet, so that means the air compressor, plant air compressor is providing that air to shock those bags or to knock the dust off the bags. Here's your screw conveyor to convey it to the drum. And then as you see here, here's the exhaust fan that pulls up to the back side of the baghouse. As you pull the dust into the stack, it's going to fall down through. Here's your high velocity air. It hits the louvers, your minus 100s will fall, your minus 200s will move on into the baghouse. As the dust moves into the baghouse, it will cling to the bag. This is your dirty air side, and it will push the clean air up through the top to the clean air. Here you see the blow pipes pulsing down into the bags, and what they're doing is it's shocking that bag and knocking that dust off. So here's an illustration to show that. As it falls down into the hopper, you can see you've got the hopper screws conveying that material back towards the drum. And there can be lots of different screws on the outside of that drum. It can be waist screws, lots of different screw configurations. Here's a breakaway of an airlock. You can see that here's the -100s and 200s put into the airlock. The reason the airlock is in place is basically because you want to keep the air away from it. You don't want to pull that dust back out of the screw. You want to convey it to the drum. Also, it allows you to keep surging at a minimal. Here's another view. If you remove the blowpipe and you can see the bags, this is something you would want to inspect when you're getting ready for a stack test. You want to see if you've got any dust on the top of that tube sheet. Just kind of a quick representation of how you would change a bag. Cage pops in, you would put your blowpipe back into place. And here's an animated view of that. You can see the dirty air coming in. You can see the dirty air coming up between the bags. And as we're pulling suction on that, we can see the clean air coming up into the clean air of the plenum. And then as it conveys on down, as the air moves out and it's trying to be exhausted, you'll see this exhaust go down into the exhaust fan and pulled out with the impeller. This is a different style baghouse. This is pulse jets, what we just looked at, but this is a reverse air, or a roto air is what most people call them, roto air baghouse. This roto air is a little different is that it has a sets of turrets. And these turrets, it's more of a mechanical style baghouse. It uses outside air instead of compressed air to shock the bags with. Here's a top view of these turrets. As the capacity of that baghouse changes or increases, you would need to add more turrets or you would take turrets away. Those turrets can be operated two different ways, either simultaneously or sequentially. As we continue on with the dust and we look at the different types that dust is handled once it leaves the drum, it can be either sent to a dust silo or it can be conveyed back to the drum. The most simple form of it is conveying it straight back to the drum. And that's what we see, 95% of the plants have that. As you get more elaborate with that, or if you have dirty materials, you may have what they call a dust runaround. And what dust runaround means is that you meter the dust coming out of the baghouse, and then you also meter the dust that's going back into the drum. So you would meter it both ways. Now also, when you look at dust, and we can refer to it a little different, dust is from the baghouse, mineral filler or any other additive would be a mineral filler. So we can have a little bit different systems doing that, and you can see on this particular system we have a conventional screw that's conveying it straight up to the drum, and we also have a mineral filler system. On the mineral filler system, how would you meter that? In my opinion, the only way to meter mineral filler dust is with a weighing device. Some people choose to remove the weigh pot and use just an airlock. Here's the problem with doing that. If you take an airlock that is capable of doing 15 ton an hour, that means that all of those veins in that airlock would have to be full. So if that material is only halfway full, that means that that thing's only capable of doing 7.5 ton an hour, not 15 ton an hour, regardless of speed. There's something visual there that you can't see. It makes it very hard to troubleshoot also if you're looking at a dust problem. The best way is always to do it by a weighing device with a weigh pot. And you can see here, this is what we have on a weigh pot. Now, not only are weigh pots pretty popular, and probably that's what you see on most mineral filler systems, but there is impact plates and a few other devices that are used to meter dust. They are weighing devices too. So if you can use that, that is the best way to look at the weight of mineral filler. If you look at this mineral filler system, there's a butterfly valve here at the top, which opens and discharges the mineral filler into the weigh pot. You would take a weight here, and then airlock is turning here, discharging it into the drum and introducing it into that screw for the drum. Continuing on to the wrap bins. Wrap bins have become very, very popular over the years, again, because of it's green. Most of the time, 20 years ago, you would have had one wrap bin per plant. and you may or may have not used that plant. You used it at your plant. Then it became more common to see 2 wrap bins, but now it's not uncommon to see 3 or 4 wrap bins. And they can take it a lot different ways. They can really put in RAS and some other things, and we're going to talk about that. The bin configurations on them are very, very close to what you see on a co-feed bins, but just slight modifications to help with the flow, because wrap sometimes is a little harder to flow with. If you look, one of the major changes that you will see is it has a flat bin wall. Again, reducing the amount of drag that you will see. One of the things that you see with wrap, as weather gets warm or you get big changes in temperature, that will affect how that wrap sticks inside that bin. So having that straight wall allows that wrap to flow better. Another thing that you will see is that the conveying belt at the bottom of that feeder is much wider. Usually it's going to be a 36-inch belt, and you also still have the adjustable gate. Again, it's all there to allow that wrap to flow more freely. As far as the conveying system, you still have a wrap Weybridge. That wrap Weybridge is going to follow the virgin Weybridge. It is the combined weighing for all of the recycle bins. It also has to have the combination of weight and speed. So you've got a weighing idler or a load cell, and you also have a belt speed tack or an encoder. It also requires alignment and calibrations. Sometimes scale factors or constants is what people use for that. And the wrap Weybridge is secondary to the virgin Weybridge. So if there's ever a question asked, the wrap's always going to follow the virgin. If you get a deviation in the virgin, then you're going to see a deviation in the wrap Weybridge. More about wrap, one of the things that you see more and more of is people fractionating wrap. And basically what that means is you're treating it like an aggregate. You're treating it like a virgin aggregate. And what you can do is you can crush it and you can fractionate it up into distinct sizes, like 1/2 inch minus, 3/8 minus. At those different fractionations, you're going to see different AC content. Another thing we're seeing is higher wrap percentages, up to 65% wrap. Sometimes we even see a few people pushing it to 70 and 80. If you go over in Europe, you see a few 100% wrap plants. But most states regulate now somewhere between 15 and 30% according to what state you're in. But if you're on private jobs, it can go all the way up to as much as 65. RAS is another item that some people talk a lot about. It's recycled shingles or tear-off shingles, like coming from a manufacturing facility. There's several different ways to do that. You can use a conventional recycle bin for that. It makes it a little bit more difficult because usually you're putting in a very small percentage, less than 5% of the total mix of the plant. So when you start conveying those real low amounts, the turn down on any type of device is always the most difficult to control. So when you try to turn down a cold feed bin that's capable of putting out 140 tons an hour or more down to 4 or 5 tons an hour or 10 tons an hour, sometimes you can have some problems doing that. What you see a lot of people going to is more like a mass flow system, kind of like what you have on a mineral filler, where you're actually using either a weighing belt or you're using a weighing bin that's on load cells. And you can see here's the conveyor taking it straight up into the drum and introduced into the drum. Moving along to the other items here, this is a tank farm. Several items you will see in here. You've got your asphalt tanks. Could have your hot oil system here also. You've got unloading pumps. You got multi-circuits for different, like if it's on the silo or the other parts of the heat. Here's the asphalt pump skid. If you look on the left-hand side of the asphalt pump skid, that device there is a calibration tank. As far as from a safety standpoint, that's probably one of the best inventions that we have seen in the industry, in my opinion. Years ago, calibrating AC was dangerous. Doing it into a tack truck or doing it into a tanker, you put someone in harm's way very easily. Having these calibration tanks really minimize the risk to the operators and to plant people in general. Most of these calibration tanks, all manufacturers build them. All of them hold right around 1,000 gallons. That 1,000 gallons is somewhere between 4.3 and 4.4 tons of AC. use them as you should. Put 3,000 or 4,000 pounds in them. Don't underutilize them and put 400 or 500 pounds in them. One of the calls that we take a lot on troubleshooting AC calibrations is that they're not utilizing the calibration tank properly. And they're using it at a very low tonnage or very low pounds, like 500 pounds instead of 3,000 or 4,000 pounds. You have different configurations for pumps. Our pumps we use most of the times are pumps pushing pumps. And here's an exploded view of that. You can see the two pumps, the strainer, and you can see the jacketed AC line. This is a view of one that's going to actually go to the plant. You can see the two distinct pumps. You can see the divert valve here. Some people call it the triac. You can see this is the pushing pump on the bottom. The top pump is the metering pump, and that metering pump has a tach on it. So we're getting that tach signal or that encoder signal back into the control room for the process control to make mix. This pushing pump, the main difference, these two pumps are going to be the same pump. They have a plate on the back side that allows one to have a bypass on it. Your pushing pump will always have the bypass. Your metering pump will not. It'll have a blank flange on the back of it. So that's one way to tell that. Also, your pushing pump's always going to be the one hooked to the motor. One of the things that you see commonly troubleshooting these pumps, if you get a plug in a line or something like that, you'll go out and you will just do a visual check, and you can look at the shaft on this pump and you say, hey, I'm circulating at half the speed of the pump. This shaft is turning very, very, very slow, and this shaft down here is running very, very fast. Sometimes you can look at it visually and you can say, hey, I can see that. Most of the time that's going to lead you to the indication that this pump is bypassing for some reason, either one for a worn pump or for a plug in the AC line somewhere. It's relieving itself to keep from blowing the packing out of the pump. As we talked about, pump pushing a pump has a tach feedback. The pump does require calibrations. One of the things that we see more and more in the industry is a micro motion or a Coriolis meter. The asphalt control is secondary to the virgin and to the recycle. These micro motions that we're talking about, as far as accuracy, they are very, very accurate. And we're going to show you a cutaway of them here. There is some states, California, the only state that I can think of right now, I think Illinois in some of their areas they have it also, is that they require by the state to use a micro motion. Any type of liquid, including water if you're using warm mix or if you're using additives, have to be done with that style meter. They are very accurate. Here's a kind of a breakaway of one that we have at our facility. You can tell it's pretty simple, not a secondary pump. The AC enters in, flows through this line here. You have these two pipes that are acting like tuning forks. And these tuning forks have sensors on them, and they can actually sense how much AC. They do a couple of different things too. They also look at temperature compensation, and they can come here's a better view of this sensor that you can see here. That particular one is one on the tuning, and we also have the temperature change. One thing that's nice about those is that we talk about how accurate they are, but also they do temperature compensation on the fly. Very, very quick result, but again, very, very expensive unit. But I thought it would worth showing because there is some in the area. When you talk about these meters, if you talk about cost, they're about 3 times the cost of a pump pushing a pump. So that's one of the reasons that we see most manufacturers stay with the pump pushing the pump system because of the cost. About 3 times, you can buy 3 pumps for about what the cost of one of these micro motions.